Hello everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering one of the most important distinctions in the whole subject, the difference between discrete and continuous random variables, and why that distinction determines which mathematical tools you use. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to the family fortune. Today he's trying to sort out whether the number of hands he wins in a poker session and his total net winnings are actually the same kind of problem, because he's been treating them like they are, and his estimates keep falling off. He opens another one of those mysterious letters. We begin with something that sounds simple but is actually doing quite a lot of work. Before you can talk about the different types of random variables, you need to be clear on what a random variable is in the first place. A random variable is a function that assigns a numerical value to each outcome in a sample space. We write random variables with capital letters, x, y, and z, and we write the specific values that they take with the lowercase version of those letters, lowercase x, y, and z. The function framing matters. Before an outcome is observed, x can end up being any of its possible values. After the outcome is observed, x is taken on a specific realized value which we denote lowercase x, and the uncertainty is gone. The function itself never changed. What changed is that you now know which input is being received. In finance, random variables show up everywhere. For example, tomorrow's return on a stock is genuinely unknown right now. We model it as a random variable, where r equals p1 minus p0 divided by p0. p0 is today's price, which is known. p1 is tomorrow's closing price, which is unknown. Before the market closes, r, the return, is a random variable. It could end up anywhere. After the close, though, r takes on a specific realized value, which we denote lowercase r. Treating it as a function from outcomes to numbers is what lets you do the algebra, calculus, and probability theory with something that is currently uncertain. Now, there are two fundamentally different types of random variables, and the distinction shapes everything that follows. A discrete random variable takes on a finite or countably infinite number of values. The essential feature is that you can list all the possible values. Even if the list is infinitely long, the values are separated from one another. There's always a gap between adjacent values, which means you can always name the next one. A continuous random variable could take on any value within an interval. The possible values are uncountably infinite, meaning any two values you could name, there are infinitely many others. There's no next value. The space is dense. So for example, between 1 and 1.1, there's an infinite number of values. The distinction is not just a classification exercise. It determines which formulas apply, what questions are well posed, and how probability is computed. Let's make this a more concrete example. Consider two quantities that we would keep track of if we were managing a bond portfolio. Think about the number of bonds in the portfolio that default over the next year. If the portfolio holds 200 bonds, the number that can default can only be 0, 1, 2, 3, and so on, all the way up to 200. That is a finite list. Every possible value sits at a whole number distance from the next one. You can enumerate through all of them. The number of defaults is a discrete random variable in this setting because it is non-infinite, and the possible values have a clear ordinality. Now think about the total dollar loss the portfolio suffers from those defaults. When a bond defaults, the actual payout to the holder depends on the recovery rate, the fraction of face value recovered in bankruptcy. Recovery rates are not locked to a whole number or penny increments. A bond might recover 43.7 cents on the dollar, might recover 61.2 cents. The total portfolio loss, which aggregates those recovery shortfalls across every defaulted bond, can end up being at any value in a continuous range. There is no next value for the loss because percentages take on an infinite number of values. That makes the total loss across the whole portfolio a continuous random variable. Here is why that difference has teeth. If you want to know the probability that exactly 12 bonds default, you can answer that. For a discrete random variable, you can assign a specific probability to the event x equals 12. That is a meaningful and answerable question. But if you ask what is the probability that the total portfolio loss is exactly $2.3 million, not 2.3 million at 1, not 200, 299.99, exactly 2.3 million, the answer is 0. For continuous random variables, individual points carry no probability. Only intervals do. So the question you actually want to ask is what is the probability that the loss falls between $2 million and $3 million, for example? That ends up being a question with a real non-zero answer. The exact point questions do not. There's one more thing worth addressing because it comes up almost every time. Stock prices trade in discrete increments in the real world, penny ticks in most markets. So shouldn't stock returns, which are just ratios of prices, also be discrete? Well, technically, yes. In practice, we always model them as continuous. First, the number of possible price increments is enormous, and the gap between adjacent values is so small that it makes almost no difference at any scale that matters for probability statements. The continuous approximation is indistinguishable from the discrete reality. Second, the mathematical tools for continuous random variables like calculus, integration, and normal distributions are far more tractable than summing over thousands and thousands of individual prices. The continuous version of the problem is so much easier to work with. Third, and most importantly, the theoretical framework that all of modern quantitative finance is built on assumes continuous distributions throughout. Option prices, portfolio optimization, risk models, all of it assumes continuous distributions of stock returns. The penny tick reality is the physical fact, but the continuous model is the working tool because there's so many possibilities. So when you encounter a new random variable and need to classify it, ask yourself one question. Can I list all the possible values, or is there always another value between any two that I pick? If you can list them, it is discrete. If there is always something in between, it is continuous. Danny sets down the letter. He's been thinking about his poker sessions as only one kind of problem, with fixed estimates, odds, and likely outcomes. But the number of hands he wins in a session and his total net winnings are two different types of variables entirely. The number of hands he has won is discrete 0 wins, 1 win, 2 wins, up to however many hands are dealt. But his total number of dollars that he ends up having as his return is continuous. It can land anywhere depending on bet sizing and how individual pots end up playing out. He has been applying the same rough intuitions to both, but that ends up being part of the reason why his estimates keep landing wrong. The frameworks are not interchangeable. So that is random variables. A random variable is a function that assigns numbers to outcomes, and there are two fundamentally different types. Discrete variables take countable values, you can list them, and individual values can carry probability. Continuous variables fill an interval. Points carry no probability, only intervals do. The distinction is not cosmetic, it determines which tools apply. In the next two videos, we are going to be going through how to build those tools. First, the probability mass function for the discrete case, and then the probability density function for the continuous case. The two frameworks are parallel but not interchangeable, and by the end you'll see exactly why.